Good evening, everyone. I welcome you all to today's webinar on geosynthetics in landfills and containment structures and effective construction quality management. Thank you, Mr. Nilantha Herath, for accepting our invitation and volunteering to do this presentation today. I would like to provide a brief outline of how today's webinar will be going to conduct it. The webinar will begin shortly after my introduction. The presentation will run for 45 minutes. We kindly request that you to mute your microphones during the presentation. At the end of the session, there will be a Q&A session. You may also type your questions in the chat box during the presentation. Attending this webinar earns you 1 CPD hour. At the end of the webinar, we will display a QR code. After scanning it, you will be directed to a post-webinar survey form. It's a short and quite straightforward form, so please fill it out and submit it, especially for those who need a CPD certificate for their participation. Now I would like to give a brief introduction to today's presenter. Mr. Nilantha Herath, a scientist who has years of experience in geotechnical and geosynthetic area, with a focus on the supervision of geosynthetic liner installation and construction quality testing, particularly for critical infrastructure projects such as dams, landfills, and highways. His expertise is pivotal in ensuring that these projects adhere to stringent quality and safety standards. In the context of dam construction, Nilantha oversees the installation of geosynthetic liners, which play a crucial role in preventing seepage and maintaining the structural integrity of these massive structures. His supervision also ensures that the liners are installed correctly, safeguarding the dam's functionality and longevity. Nilantha graduated from the University of Peradeniya in 2001, specializing in physics and chemistry. After that, he completed a postgraduate diploma in environmental sciences from the University of Peradeniya. In 2005, Nilantha joined RMIT University in Melbourne as a sessional teacher in soil science. He then joined Terra Firma Laboratories in 2008, where he worked as a geotechnician. Since 2016, he has been working as a project manager for geosynthetics and liner integrity assessment at the same company. Right, so today, Nilantha is going to present us about geosynthetics in landfill and containment structures and effective construction quality management. Okay, now I hand over the floor to Nilantha, now to you.
Thank you, Darshani, and I hope this is going to be a worthwhile presentation for all of you. So thanks for the nice introduction. So yeah, so the baseline is I predominantly studied science and work related to science, but after migrating to Melbourne in Australia, one of the jobs I accidentally encountered, I didn't have any engineering background, but I ended up landing in a materials lab, which is accredited materials lab who's testing rocks and soils and materials. So as a part of that, the laboratories, especially in Victoria, the laboratories are, most of the construction projects has the construction quality assurance is preferably done by a third party. And that third party is independent from the designers and the principals and the construction companies. So it's a nice setup. The setup in Australia differs from state to state, and Victoria has been one of the states where you have some strictest regulations, especially when it comes to the containment structures and landfills. And so in Victoria, we have this guideline called BEPM, or the best practice of landfill management. And I think it's it'll be a good thing to mention that this 2009, the BEPM system was introduced to EPA in Victoria by Kapila Bogada, who's a geologist from Peradeniya University. And then this has been followed by a lot of the other states. So when it comes to geosynthetics, so our involvement is from quality management and supervision of different stages of construction of different landfills and containment structures. Landfills are commonly the structures that you normally use to put the municipal waste, your food waste, or your day-to-day waste. And the other containment structures are chemical ponds, tailings dams, mining ponds, and all those different types of structures. So the containment structures.
Nilanthil, can I interrupt you, please? Can you please put the presentation into the presentation mode?
Okay. Yeah, good.
Right.
Yeah.
And others, could you please make your mics mute? Jai Siri, I think some ambient noise is going on. Thank you. Yeah.
Yeah.
Thanks.
So
Thanks.
so the topic we selected is geosynthetics in landfills and containment structures and how to do the quality management. And it's a broad subject. Geosynthetics is been everywhere especially during the last 20 years. We could see an immense, like a big development in geosynthetics, replacing a lot of structures, a lot of rock structures, metallic structures, purely for the convenience of installation and low-cost materials. But geosynthetics has been used increasingly for a lot of different aspects, and landfills and containment structures have been one of the main areas where the geosynthetics are being used in today's world. So what are geosynthetics? This is so I think all of us know a little bit about the geosynthetics, where everybody, all of us have been using geosynthetics or have been exposed to geosynthetics knowingly or unknowingly at some stage on our, especially as engineers, I think. But geosynthetics can be identified as polymeric, that means synthetic materials predominantly made with plastics, that are using in connection with the geotechnical applications, civil engineering structures, roads, containment structures, embankments, and a lot of other areas. The modern geosynthetics applications started with the fabrics being used for bearing capacity improvements in the early 1900s. This is the documented history. But the ancient engineers could have always have used fabrics for constructions. I've seen some old stories about how they used in the ancient construction of the old structures in Egypt and Asia and a lot of other places. The modern application of the geosynthetics started, I think, somewhere in 1900s, when, especially in USA, when they started using heavy grade, strong fabrics to manage soft soils when they want to build structures like buildings and highways on top of soft grounds. Now, as a geotechnical person who's working with a geotech company, we know that we are involved in a lot of building a lot of roads and highways, and or sometimes building pads. And most of the times, the name of the game is that you got to go and find hard ground and then build up on top of that one. But however, when going down doesn't mean necessarily you're finding hard ground. If you're going to hit your groundwater, if you're going to hit the soft soils, that's where the geosynthetics comes in. So thick grade geotextiles have been used since for about 100 years now to improve the bearing capacity, where you place them and then start placing your fill, your soils and rocks on top of that one. So that's a brief history of how the geosynthetics came into use. But I think as a Sri Lankan, I always argue on this matter. When we use some clay houses, like the typical houses, when we use the clay into the when we put the clays into the walls, what it should be, and you know how you use the clothes wrapped with mud, putting into that one. I think that's another use of geosynthetics, although we don't call it the initiation where we started the geosynthetics, but I think like probably we would have been using geosynthetics many thousands years before the where it started in USA. Application of geosynthetics. We use it for retaining walls, very high retaining walls, without using the metal and rock structures, or in conjunction with the metal and rock structures. The ability to use lightweight but strong plastic reinforcing materials like geogrids and nets have been helping the retaining walls and the retaining structures for a long time. Roadways, if you ever think about when you are traveling on a swampy area where you are traveling, where you travel on an area where it's predominantly swampy, soft soils, and how is this whole road I am traveling is holding up without going down or deflecting, and most of those cases geosynthetics are involved in different modes. Erosion control, that can be the drainage controls by using different types of drainage nets and drainage applications. Predominantly the structures people used to use perforated pipes wrapped with the textiles or wrapped with the rock blanket is being replaced by, in most of the applications, in very simple, ready-made geosynthetic strip drains and the structures. This is not today's topic, but I thought it's a good thing to share a few things about the other uses of the geosynthetics. Containment structures. This is our topic today. Containment structures, landfills, tailings dams, chemical ponds, effluent ponds, leachate ponds, whatever. It can even be containment of the drinking water and the drainage applications. Leak detection applications. This is a new area where the geosynthetics are coming up. I have added a couple of slides at the end to describe some of the high-end leak detection techniques, some of them that are being used as a part of quality assurance, and conductive polymers, conductive geosynthetics have been increasingly used in structures. So when something happens, when a leak happens, you will know where the leak occurs without going into investigation with the electronic systems. But I think leak detection is a separate subject by itself. It's a topic for another day. PFAS is increasingly becoming a hot topic. Poly and perfluoroalkali substances. That's been found in a lot of firefighting chemicals, lot of non-stick coatings. Now people have the understanding that PFAS can create long-term and short-term health impacts for the people. So modern day geosynthetics have a big emphasis on. There are a lot of research and development, especially in Melbourne, going on in developing new geosynthetics that can trap or filter and manage PFAS. And I'm pretty sure as engineers you must be aware of the increasing awareness about PFAS. I think it has always been there, but it's only now we have started talking about that one. It's only now we have started to understand what it can do, how do we test it, how do we contain it, and it's a big topic going on in here. But the modern geosynthetics has a big emphasis on how we can use the geosynthetics to manage PFAS. A simple usage of a material. You can see earthworking machines, a bulldozer going on in the background. Now you have a geotextile line on the floor, and then you have a thick rock material placed on that one. It's a typical use example of geosynthetics. What's underneath the rock and the fabric is a plastic membrane that will prevent from contaminated materials going into the ground. In this case, a thick grade geotextile is being used to minimize the harm or protect the harm of this rock. This is ideally a 40 millimeter coarse rock, coarse aggregate. So the big machines traveling upon this rock layer can put pressure onto the plastic membrane. So the plastic membrane is protecting the stop working as a barrier to stop the contaminated waste going into the ground, but the textile, which is the gray color thing where the person is standing on, is a cushion material that's protecting it from the impact of the rocks. And also the person who's standing here, that's someone who's looking after the quality assurance. So it's a very common thing in here. Whatever you are having, there is a reasonable amount of supervision by people who have the experience to supervise, to see whether there's any impacts that's happening in an environment like this. One simple other example, geogrids used as a stabilization layer under the pavement. So soft subgrade, soft grounds before you place your materials. Two big geogrids have been plastic grids, very lightweight but very strong, being applied on the road before you put your next layer of. So this plastic grid will work as a unit, improving the bearing capacity, so the materials won't sink into one another, and then in the long run, control the deflection of the shape of the pavement. Typical example, geotextile is used under the pavement as a separation layer. So this layer, which is called the geosynthetic, so in your left-hand side, you can see a road that's constructed without the separation geosynthetic layer. This is ideally a heavy grade a geotextile, where you can see the materials, the lower subbase, the clay material, the rocky material from the top invading and getting into the soft material, whereby you can see the deflection happening upon traveling. On the right-hand side, what it has done is the geotextile is stopping. In this case, we call that the geotextile is acting as a separation layer. So separation layer acts, so it stops the aggregate on the top layer, pushing into the lower clay material, whereby it's maintaining the shape and the shape of the formation. And in the long run, what you get is a proper road that will last years and years without having to repair the roads. Landfill and containment structures. This is the main topic we are going to talk today. Landfill and containment structures. The main task of a landfill. Just to be clear, the landfills I'm talking about is the rubbish tips. where we put the municipal or where we put the waste. It can be clinical waste, it can be chemical waste, it can be some other waste. So purpose-built facility where you can store the waste in a way that the effluence generated by that one is not going into the groundwater. So the mainly when it comes to the landfills, the main threat is not the waste. Your good old days, you dig a hole and then you used to put waste into a hole, and that's no problem. But the problem issue starts when it starts raining. Raining creates leachate by washing off all the decomposed or chemically contaminated material, and it creates that liquor we call the leachate. And that leachate, if that leachate goes into the ground, it will create contamination in the groundwater. And that's the reason why in maybe 100 years back, people accidentally started finding out that everyone around a landfill will start getting sick. Their water, their groundwater or their taps, their water supply started getting contaminated, and it took a long time for people to bring. Number one is to understand why it is happening. Number two is to bring out the right procedures, experts, and the legislative controls, so you can stop doing that one. So every locality needs waste management. Every place, every country, every area needs a landfill or a containment waste containment facility, and you need to have them pretty close to the locality for the sake of easily transporting the waste. You don't want to pay take the waste from one house and drive 100 kilometers into a remote area to dump that one. That practically, economically, it's not viable. So most of the landfills are there. They are within a certain range, less than a kilometer away from civilization. But the geosynthetics, I mean, proper engineering techniques and especially geosynthetics have been used to contain the effluents. So so general waste or leachate. So there can be ponds where you generate leachate. Leachate can be coming from a hospital, chemical waste, a chemical factory, a tannery, like where you process leather and things like that, where you get all these nasty chemicals. Then you have specific chemical storages, like here in a lot of places in Australia, you have specific purpose-built big storage tanks where they store things like sodium hydroxide, caustic soda, heavily corrosive material that you don't want anywhere near your groundwater. So there are specific geosynthetic applications, geosynthetic layers and materials being used in these containment things. Clinical and contaminated waste, drinking water, irrigation water. Especially, I'm familiar with a lot of areas in Australia have lot of areas where you get rain only a few times a year, or maybe once a year, and then you don't get nothing after that time. So a lot of people build big irrigation dams and try to protect all the water that they can. So it's a drinking water or water storage facilities. They are also being lined with geosynthetics. Mining waste, we do a lot of work with mines. So typical mines, one example is if it is a gold mine, you go down, you excavate, you bring the rock. Gold is predominantly trapped between the quartz veins. So you crush the rock and then leach it with sodium cyanide. The gold, so that's how you take the gold out. But as a result of this one, you get sodium cyanide contents, cyanides going into the water. So if you are doing a gold mine, you are not allowed to put your mine waste anywhere. So you got to build specific huge, almost like landfills, to put your process waste, solid and liquid. And also when you are deep, like you go down digging, mining, and one problem you have is that you have water underneath. So dewatering mines is it's a big subject in mining. So you always have to pull your water out. So dewatering, but what comes with the deep lying groundwater is chemicals like arsenic and cyanides and other things. So again, you can't put it on. So a lot of mining sites, they are maintaining huge, like I'm talking about things like 200,000 or 400,000 square meter big tanks or the dams to put their tailings and the processed water. Commonly used geosynthetic materials. Geotextiles, we just had so geotextiles is just like the fabrics, like a blanket or thin or thick materials being used for various purposes. It can be cushioning, it can be filtration. Geonets are drainage nets. You use it for drainage control of the sidewalls. Geogrids, I think we had a photo earlier of how you're placing the geogrids before you place the form of the rock on the highway or the road you're building. So as bearing capacity enhances. Geomembranes is one of the most common. I mean, geomembrane is the most common material that's been used in the containment structures for its ability to retain, to contain liquids without allowing it to leach into the groundwater. Then you have geosynthetic clay liners. There's another couple of extra slides. We can come to that, explain that one as we go. Drainage nets and composites and geowebs and geocells. They're all different names, fancy names, but many different applications that you use in the containment structures for different purposes. What are geosynthetics made of? A lot of geotextiles are made with polypropylene or polyester and geogrids as well. Polyethylene is the main material where you use the geomembrane or geonets. PE, polyethylene, high density and low density, and there are different grades. That's been vastly used to do dams, containment structures, tailings dams, landfills, for you name it, for every different application. You also have PVC used in geomembrane. Geomembranes are a separate subject that you can talk for hours and hours. There are, depending on the chemical composition, there are different geomembranes that are catered to store different type of materials. GCL, made with polypropylene or polyester geotextiles with a mixture of clay, geosynthetic clay liner. Then you have activated carbon with clay, increasingly being used. Then again, all these ones we can talk longer. I think this is not the time, but activated carbon is being used in the GCLs for PFAS related control applications. Then you have clay with polymeric additives to enhance swelling ability of the GCLs. Structure of a typical landfill. I'm looking at the clock here. Okay. Typical structure of the engineered landfill. You can see landfill has the baseliner, waste being placed. You have a leachate sump. So the sump collects the leachate, and you have pipes connected to that one to connect that one, and you have waste placed. And another significant thing about the landfill, especially the municipal waste landfill, is that you have decomposable materials. Upon decomposition, it generates landfill gas, mainly methane. And this methane is a problem. It has explosive qualities. But if you so there's a big emphasis at the end of the life cycle of the landfill to cap it. And capping is a different process where you make sure that no water is going into that one generating leachate. At the same time, you have applications to trap the gas and take it out. And if your landfill is big enough, then there are a lot of landfills in Australia where they use that gas to generate electricity. And I know there's one city council that probably something smaller than many times smaller than Colombo, but their landfill gas, after about 4 landfill cells, it's generating enough power to run their council buildings, so municipality buildings. So that's that's something that that's going to waste being used with the proper applications. Geomembrane. Polyethylene is the most common material. Main containment barrier, most commonly used containment barrier is the geomembrane. Impermeable and has a long service life based on the make and the additives. So that's another topic again. When you are using corrosive materials, highly oxidative materials, the polyethylene resin, obviously, the raw material comes from the petroleum industry. Most of the times it's coming from the Middle East. So the polyethylene is mixed with a lot of material like carbon for strength, and then a lot of antioxidative materials being used, so it will withstand the corrosive or the oxidative nature of the material what you are going to store in the landfill. So additives is a different subject, but depending on how the geomembrane is made, it can have a very long medium to very long service life. PVC is another material. Bituminous geomembrane is increasingly popular application in containment structures, but not so much in the landfills. This is mainly for the mining waste tailings dams. Bituminous geomembranes is a heavy grade geotextile, like if you are dipping it in tar. Right? So you're putting it in a solution of bitumen, so it will be an enhanced, thicker material. So increasingly becoming popular in especially the hot parts where the polyethylene geomembranes get wrinkled when you're placing it. Then you have reinforced geomembranes with the polyester grid inside that one. Typically, geomembranes comes like this. These are rolls. These rolls are about 8 meters wide, 7 to 8 meters wide. Can be about 150 meters long, and this is how you deploy them for someone who hasn't seen them. So the machine holds the geomembrane, and these people they're using a metal clamps onto that one. They are pushing it down and place one another. You overlap it with about 150 meters, 150 millimeters, and then you weld it with a heat welder. It's like a laminating machine. This is called a dual wedge welder, and these welding techniques are becoming very sophisticated. This particular welding machine can so there are things. So the hot wheels are pushing the top and the bottom layers together. At the same time, it applies heat and it applies pressure. So this is called a fusion welding. So that pressure and heat makes the two polymer sheets, two geomembrane sheets melt and fuse together. So it's called a fusion welding. And once it's done, it becomes more stronger than the natural material. So this is called a dual wedge welder, and these welders can be programmed with the speed and temperature and everything. So in a very hot day, you will run it low temperature slow, and very cold day, you will be run it very slow but high temperature. Geosynthetic clay liners, GCLs, polypropylene geotech, so high quality bentonite clay sandwiched between two geotextile layers makes GCL, which is geosynthetic clay liner. It this is something that's developed after geomembranes. So what you do is you have bentonite. I think if you are familiar with bentonite, bentonite is a naturally occurring clay which has a very high swelling ability, which has a liquid limit about, it can go about 200 to 300%. Like imagine like normal liquid limit of a normal clay where it turns into mud is maybe 20% or 30%, something like that. If you have high fine clay, a lot of slimes, sometimes it can have a bit of a higher level liquid limit. Whereas the bentonite can have maybe 3 times of like 300%. So 3 times of its own weight of water can be absorbed and swell. So the main way is once liquid or water gets into that one, it swells and it creates an impermeable barrier. It's easy to install, and it's more impermeable than a clay liner. So most commonly used sodium bentonite for the high swelling capacity. It's permeable. So normally if you use a very fine clay and then you compact it, you normally get, if you are familiar, a permeability around 110 to the minus 9 meters per second. Whereas, so you normally install about a 1 meter thick clay liner in a landfill, whereas you can get the same impact by using like a 1 centimeter thick geosynthetic clay liner rolled material. The bentonite activates upon water absorption and swelling, and leaking fluids will trigger the hydration. Normally, this is installed under the geomembrane. If the geomembrane has a physical puncture and it starts leaking, the GCL will make use of the leaking fluids and plug the hole locally. This is the same material you use for drilling fluids and also boreholes and other things to cover the edges. So the same material, but in the powder form. Certain limitations are there depending on what ions present, divalent cations and other things are affecting the swelling ability. It's another topic. GCL is for another day, I think. Typical cross-section look of a GCL. So you have that black geotextile at the bottom. This brown stuff is granular bentonite, and then it's covered with the top textile, and it's stitched. You can see the right-hand side one. You can see the cross-section. You have the bottom geotextile, top geotextile, and then you have the bentonite inside. So this is in the dry form. So you can, this is only about 1 centimeter thick. You can install it very easily, but it gives the impact like a 0.5 meter thick clay liner upon installation. It's costing, but I think the convenience of installation helps you to do that. So some example of how much it can swell. A small amount can swell a lot of up to a big volume. Typical containment structure, you can see this white material is the GCL. GCL is being installed on the subgrade, and it's getting covered by the geomembrane. So geomembrane, you can see how the size of a geomembrane, about 8 meters wide, long one. You are using it by using an excavator. Geotextiles, they are used as a cushioning or protection layer in containment structures, maybe separation or drainage structure in the roads. So as a filter material made out of predominantly polypropylene or polyester are the common used one, that there are other materials as well. Thicker materials for puncture strength over the geomembrane. So if they are heavy grade ones, if you need the numbers, something like 500, 600, 700 grams per square meter grade geotextiles for the cushioning, whereas thinner grade textiles are for the filtration applications. This is again the same photo, but it's about the application as a cushion. Quality management. A few more minutes. Okay. Quality management. So you got to have quality. Like these materials are expensive, specifically made for the purposes, but you need to have a good quality management system so you can make sure that you are buying the right thing, and the people who are installing that is adequately qualified and they do the right thing, and then nothing happens in between the installation, physical damages and things like that. Darshini, I think can I have another 5 to 6 minutes?
Yeah, sure, Nilantha. Yeah.
No problem. Okay. I realized that. Okay. So, each quality management, each project has a technical specification guideline that tells you how to install every layer, how to install the materials, the standards you have to follow. Materials selection criteria indicated. How do you select the right geotextile, right geomembrane, the right GCL for the intended purpose? That meets the design intent. And then internationally recognized standards and guidelines are in use. So it's easy to say, okay, your geomembrane has to satisfy this standard. So there's the standards going on everywhere. So you can use those ones to, it's very easy now. It's universally accepted. All what you need to know is you got to use the people who knows about the guidelines. Construction quality assurance system and a plan. Every structure, every containment structure, construction of that one, no matter how good your materials are, no matter how experienced your people, no matter how good the design is, independent quality assurance system and the people who are working on looking at all the aspects is paramount. They do a good service. That will combine all the little things together to give the right results at the end. Now, when it comes to the quality assurance, these are a few things. Geosynthetic Institute, GSI, GRI, you can browse them over the Google. They've been making methods, manufacturing methods, testing methods, installation methods over a very long time. GSI and GRI, and GRI makes guidelines. Like 2 examples is GRI GM13 is about what should be the ideal quality of your geomembranes. These things are available free. I put the under point D, that link gives you about the all the links of all the GRI documents. So that tells you what do you normally expect from a geomembrane, from a GCL, from a geotextile, all the different types of things. Then you use internationally recognized test methods, ASTM, like I think like SLS we use, predominantly we use here ASTM, American standards, British standards, EN, ISO, and they all are interlinked. Depending on where your material is originated, you are being tested and QA'd under that one. But it's easy to match. If you do a test in Australia, you can match it to the same thing, the same material, same parallel standard, and interpret in the local terms. Laboratory testing, few examples: tensile strength, Australian standards 3706.2A or B, that's for the tensile strengths of the geotextiles. Permeability of the geosynthetic clay liner, ASTM-D, so this is American standard, ASTM-D 5887. Swelling capacity, ASTM value. Puncture strength is a test that you drop a sharp cone, a 1 kilogram calibrated weight sharp cone with a calibrated angle of the point, dropping with a calibrated height, and see what sort of a hole it will make. So it's a universal system. You check that method and you can test any material come from anywhere, and then you can interpret in the local terms. CBR, or the bearing capacity, Californian bearing ratio, which we use for the assessment of the bearing capacity of the soils. There is a method adopted, the same principle being adopted to measure the bearing strength of a geotextile. So that's 3706.4. Just few examples. But I think because the whole idea is these are the keywords, you will be able to find out a lot of information regarding that one. Liner integrity assessments, this is one of the, I won't say new, it's been happening for a long time now, but it's becoming mandatory now. If you install plastic membranes, so the membrane is made with top quality material, the top quality installers making the installation. But anyhow, when 20, 30 people working on that one, people walking on the membranes. And sometimes in here, it's a common thing, a kangaroo jumps in on the membrane, and its sharp claws sometimes can damage the membranes. So when that happens, before any containment structures being, so this is the last part of the quality assurance system. Before you hand it over to the user, you got to do leak detection. These leak detections are mainly electrical, but you also have the water-based methods. Like water balance method is you are filling up with the structure with water, and then observe it for some time and see how much of water do you lose, and to try to find how it is being lost. And then maybe colored dyes being used, and you're trying to inject from one point and then see whether it's coming out of another side. But there are time consuming methods. This is one. I mean, I try to put few examples. This is the dipole survey method. This is a geoelectrical survey method, which is basically this person is carrying equipment. So they are walking on a rock-filled area, but what's underneath the rock fill is the geomembrane, the plastic membrane of the landfill. So this is the rock filter that collects the leachate. So you got to have the filter, but when you are installing the rock blanket with the dozers and big machines, it tends to tamper the geomembrane. So you can't see where the holes are. So obviously you are taking electrical measurements, voltages, and you can see that it has a GPS location equipment set up with that one. And that will, so on your right-hand side is what you call the voltage map. This is like, so your typical contour map has the northings, if you're using GPS, northings, eastings, and the RL, the level. So imagine you are replacing the level with the voltage of a location. It can create a similar voltage contour map, but the characteristic patterns of this map can tell you where a hole is. So you can try and find. So on the left hand side, you can see that it's been found out, and he's digging the hole to find the hole. So you can pinpoint like a 1 millimeter or 2 millimeter size small holes if you have the right conductivity. This is another method. It's called the ARC method. So these methods, if you can browse them, plenty of information available online. It's an electrical spark method to use. You use about 20 or 30,000 volts to find out tiny little defects, tiny pinholes in the membrane. So CQA person or the technical CQA technician or the engineer should be a suitably qualified, trained people who come and assess the construction process. How can a CQA person or construction quality assurance make it easy for everyone? Means that construction quality assurance person, by knowing the techniques, knowing the specifications, knowing the design intent, can help every party who's conducting the work to work together. And we call it the name of the game of construction quality assurance in our terms is you got to anticipate what can go wrong today. So tomorrow you won't have a lot of unhappy people. You can intervene. A proper QA engineer, QA company, QA consultant should be able to guide the others. Okay, this is how we are going to work on the next section of the structure. So a slide about experience, why you need an experienced CQA person. So in Melbourne, it has to be independent from the designer or the principal or the construction company. But it happens in different ways of so the effective good communication with the interested parties, independent CQA is important. Adequately experienced people can make the project's quality much better. Experience in the field is important. CQ construction quality assurance can help everybody to achieve the goals, and finally to meet the design intent. So I try to rush through. I don't know whether I rushed too much, but I had 36 slides, so I was trying to push this one on. I apologized if anything was unclear, but I'm happy to. I mean, we can share a lot of other information in future if you need to. So thank you very much for giving me the chance to do this. So and I think it's the time to have some questions and answers.
Thank you, Nilanthe. Thank you for giving us a very interesting and insightful presentation. I think the participants can get much more out of it. Now, the floor is yours, participants. If you have any questions to Nilanthe. I have one, Nilanthe. Have you have any experience in working with marine structures like breakwaters, revetments, where the ocean seawater get in interaction with the geotextiles?
I personally don't, because most of my work has been around the containment structures. But say in Australia, we have this organization called the Australian chapter of the International Geosynthetics Association. It's a meeting point. I think it's a good if there's any engineer who's in Australia, it's a good place to. It's a like a community organization. People get together to exchange ideas. They run a lot of webinars and other things. They have a YouTube channel. So we always come across geotextile manufacturers, construction companies, designers. So yeah, but we are aware of this is happening in very large scale. But I mean, I personally haven't been involved in one of those projects. But some simple example is that Geofabrics Australia has something called the Elco Rock, which is actually a heavy grade UV treated geotextile bag filled with soil, filled with sand or rock. And instead of just placing rock or just placing sand, you are placing these big almost like big pillows of geotextiles filled with sand or rock into the beaching areas, which has been working very nicely and very effectively. So these information are available for anyone who's interested. But not personal experience, I haven't done, but I know that they've been using them very effectively. Geotextiles have been cutting down the unnecessary costs and lengthy procedures when it comes to especially the erosion control.
Yeah. Thank you. We have quite a few questions in the chat box. Can you see it, Nilanthe, or you want me to read it? Or
yeah, it will be better if you read it, I think.
Okay, right. Nilanthe, thanks for the excellent presentation. Road pavement, within bracket flexible or rigid, placed in proximity to vegetation tends to elevate the pavement, causing undulation, which result in hazardous situation for road users. Have you had any opportunity to use geosynthetics to counter such situations during road construction projects? If so, can you provide reference examples?
Sorry, Darshini, if I read it correctly, this is also about the effect of the vegetation, right?
Yeah, vegetation tends to elevate the pavement, causing
Look, I think up to a certain level, thick grade geogrids and the geotextiles are controlling the penetrations, all the protrusions happening from the rooty materials and the vegetation that can probably can grow under the pavement. But I think when it comes to that one, it still goes into trying to get rid of most of the vegetation and all the organic materials or plant roots and all the other things going down to the waste level where you can remove them all, and then obviously use a heavy grade geotextile. But no matter what type of grids you use, if the vegetation starts growing, that's one place where we have seen the sometimes the nature always finds a way to come through. But yes, heavy grade geotextiles. That's one of the keys, but not the only way. I think that you could get rid of most of the vegetation and then install with the geotextiles.
Yeah, there's another question. What's the use of high tensile geotextile in embankment construction?
Embankments, high tensile geotextiles are being used for especially when if you're like 15. Now, when it comes to geotextiles, you got two main type of geotextiles. One is woven geotextiles, The other one is the non-woven geotextiles. So woven geotextiles are the ones typically like a mat. You can see the wefts and wafts. It's actually been, you are using high grade material, but you're actually weaving it in the form of like a mat. So you can see the lines, like one of the clothes we are wearing. You can see the lines of woven geotextiles are predominantly of high grade, high tensile strength materials. The other material is called the non-woven, which is like a blanket. If you look at a blanket, you don't see the wefts and wafts or the north and south, the line, you can't see the lines, because the way you are using the non-woven is you are using a lot of long fibers. You put it on a conveyor belt, and then you have the little metal, what do you call them? It's like a comb, like we call it the needles. They push you from top to bottom, and then it will make the polypropylene and other materials intertwined, and that makes so the non-woven ones are predominantly for cushioning and filtration. Now, specifically, you are using woven geotextiles. So two things. You got to use geogrids. Geogrids are made with polypropylene or polyethylene, very strong structures. So depending on what your requirement is, you can get them in different aperture sizes. So first, what you will be doing is, once you go down to the excavated formation, the base of the formation, you will be installing geogrids. And this geogrid will do two things. One is that it will stop things from falling out. The other thing is the geogrids will, whatever the material you are going to place on top of the grid, it creates like a housing. If you're putting a rocky material, the apertures of the geogrid specifically is helping the materials to stay strong together. So that's another way, another application of how you use on the embankment. So when it comes to the embankment, there's a lot of uses of geogrids rather than the geotextile. Geotextile, the heavy tensile geotextiles are used a lot, and for that matter, both of these materials are used a lot in rail constructions. So if your rail track is going through a swampy, like a soft soil, submerged wetland, and your geogrids and the heavy grade non-woven woven geotextiles are an essential part of the formation, where imagine, like, the rocks are stronger. Rocks are very strong compared to a geotextile, but the issue is rock is a point material. So you put a point load, point pressure onto that one, it can submerge, it can move down. How high tensile geotextile works is, the geotextile works as a unit. So as a unit, this is the same example like what we used to do in science, where you put a ruler under the newspaper and try to hit it. So the ruler breaks, it can't lift the newspaper because of the atmospheric pressure putting pressure on the surface area of the newspaper. So the same principle, you apply the geotextile, and that geotextile works as a unit. So there's, even if the point loads going from bottom and the top will be distributed among the other part of the geotextile, so which improves the bearing capacity. So they use a lot, but when it comes to the embankments, a lot of geogrids being used for the structures.
Oh, okay, thanks. I think we have two more questions, but in the meantime, I would like to share my screen that that we have the QR code displayed for them to. Yeah. So this is the QR code. If you scan this QR code, then you will be directed to the post webinar survey. So those who need to CPD certificates or anything, just or if you are interested to give some feedback of the webinar, then please feel free to go to that form and fill it up and send back to us. And in the meantime, where can I? And at the same time, I have put that QR code on the chat box as well. Next questions, 2 questions, if you can give some ideas quickly, Nilantha. Thank you, Nilantha, for the excellent presentation. In leachate holding pit of the sanitary landfills, do you use HDPE membrane or concrete?
We use HDPE because for any containment structure, I think they are moving out of they can still use concrete to create the form, create the structure, but concrete tends to crack over the time. So HDPE is much more reliable than that. So you got low density polyethylene, high density. Out of that one, HDPE is what you are using. Yeah, so pretty much sanitary landfills, the whole flow, whole baseliner, and pretty much the nowadays the walls and the floor, everything is lined with HDPE geomembrane. And depending on the water quality under your landfill, if it is like grade A, good quality water, then you got to be extra cautious. So you can see in a lot of places you have a 300 to 500 millimeter fine clay material being compacted in 200 millimeter layers. And so these things get density tested and QA, permeabilities, all the other testing done. And on top of the prepared clay subgrade, clay sub base, you are placing the GCL, geosynthetic clay liner. And on top of that one, you place the geomembrane. So when you are actually thinking of a most common modern landfill structure, you get the subgrade, then you get the may or may not have clay. If you have clay, you have about 300 to 500 millimeters of good quality clay being compacted into that one, like 95% standard compaction. And then you place the GCL, then you place the geomembrane, and then you place a thick geotextile as a cushion, and then you place like a railway ballast 40 millimeter aggregate layer across the full area of the floor. And then on top of that one, sometimes it's a bit too engineered, but it definitely does the job. And on top of the rock area, and you have a thin fabric, which is the filter. Now that's where you place your waste. So when you place your waste, when the rain comes, when it generates the leachate, leachate is all the solid matters are being filled by the separation geotextile on the top, goes into the rock layer, and landfill flow is made with like 2 to 5% slope. So everything runs into the leachate sump and then immediately being pumped out to a leachate pond, and then you treat the leachate in that one. So you do all these things, but you make sure that you don't leave any leachate to stay in the landfill in the long run. So everything pumps out to the leachate pond, and then you do your activated sludge and all the other type of treatment on that one.
Yeah, thank you. So there's another one. Do you do designs on geomaterials, and what type of loading considered?
No, we don't do the designs. So, but the loading, it depends on the purpose. Like for instance, if I understand that one as a non-designing person, now say for instance the textiles you are using on the base for the cushion layers of the that covers the geomembrane, that cushions technically need to protect the geomembrane from the rock and the waste being placed on top of that one. Now, the pressure of the waste, depending on how high the waste mass is. So if it is a shallow landfill, it can start from about 200 kPa pressure, whereas there are some landfills that has about 600-700 kPa. So then, as a result, all the precautions you are taking to protect the geomembrane. Geomembranes are typically all 2 millimeter geomembranes, but the protective layers you are placing on top of the geomembrane the strength and the thickness, bearing capacity, puncture strength increases depending on the pressure, the pressure created by the waste mass.
Oh, okay. And the last question, what's the best material for canal banks?
So if the canal banks are like, if it is containing water, now there are materials. One material namingly is called a concrete canvas. So it's like a GCL. Like, remember, the GCL is bentonite clay trapped between two geotextiles. Now there are materials where you have like something like the preset concrete impregnated, or concrete being trapped between the geotextiles, made into a roll. So you roll it out and then you wet it, and once you wet it, it becomes concrete. Like, okay, it's not a 100 millimeter thick clay like concrete layer, but it works fine with normal channels. So concrete canvas is one typical material. So these are not mainly used in the containment structures. If your material, if the channel carries material that are contaminated, you will be using something like bituminous geomembrane or or HDPE. But if it is the water carrying thing, it's a very common application that you are using this concrete impregnated geotextiles being used. So easy to install. You make the structure, install that one, add water, and it will become like a concrete lined channel. And so you do when you're doing that one, you do your testing, you do your MPAs, the crush values and other things on and the quality of the cement on this one when it comes to the quality assurance testing.
Okay, Nilantha, there's one last question, if you don't mind waking up.
No, that's right.
I know it is 10 past to you now in Melbourne.
Yeah.
So just if you can give a quick answer, what's the best one, woven or non-woven geotextile material for gabion construction along the canal?
So gabions are normally used for embankment, what do you call that? Embankment strength, right? So when it comes to the strength applications, it's always woven geotextiles are, so non-woven geotextiles can go up to about if I talk about tensile strength, so if you take something like 90 grams per square meter, non-woven geotextile can go up to about something like 100 kilonewtons per linear meter. I'm just sort of giving comparison values, whereas similar woven material can have up to about 200 or 300 kilonewtons per square meter. So woven geotextiles are stronger. So you don't use a lot of woven geotextiles in the containment structures, but when it comes to the gabions, any embankment reinstating and slope stability applications, you use a lot of woven geotextiles. But that's not the only thing. There are a lot of other applications. They are like the sidewall drainage. Like, say you have a slope, you are placing soil on the slope, and then eventually, if the water penetrates and if the placed soil layer tends to slip on top of the existing layer, mainly because the water sinks down to the bottom of the placed clay or material, and creates a saturated section between the interface of the two materials. So something called geocomposites, which is a plastic net covered with thin grade geotextiles from both sides, which is a fine thing. It's been placed on this interface. Whatever the water goes to will filter through the textile, goes into the net, and flowing in plane into wherever the desired area. So that will protect it from the interface getting saturated. So there are some other applications. There are a lot of geosynthetic applications apart from the geotextiles and grids, because one controls the strength, some of the other ones controls the water flow. So I think when it comes to that, you have to look at both aspects. Hydration and the water is one thing, the strength and the pressure is another thing. Yeah.
Okay, thanks, Nilantha. Lastly, few participants would like to have your contacts, if you wouldn't mind. I'm not sure whether if you would like to share your contacts, then would be if you can type it on the chat box. What do you think? And while you share your contacts, I would like to take this opportunity to thank Nilantha Herat for being the resource person for our today's webinar. Thank you so much, Nilantha, and for spending your valuable time with us and this night, I know. So we were really grateful for your contribution. And I think engineers today, the participants, you have, I guess you got a lot of information and knowledge for your practice on geotechnical engineering and things like that. And thank you to Nilantha. And also I thank the manager publicity at IES Mother Chapter in Sri Lanka, Chamila Priyantha, for making this Zoom space to use for us for this purpose. Thank you, Chamila. And also I would like to thank Anupa Matrarachi for connecting Nilantha with us today. And otherwise we wouldn't be able to get you in for this webinar series. Thank you, Anupa. I think he's not able to participate this webinar today. He's off-site working, but however, I thank to Anupa as well. Finally, a big thank you to all the participants today's webinar. And it has been a fantastic number of participants today, nearly 50 sometimes. I just checking the numbers. It's really, really good outcome. And thank you, everyone. And so, yeah, what are the other questions in the chat box? So, yeah, and have you shared your contacts, Nilantha?
Oh, actually, yes, I will do it now.
Yeah.
I'll put my email.
Yeah, maybe email and yeah, your name and email would be enough, I think.
My email on. Yeah, so please feel free to contact. I mean, we especially with Anupa, we have few WhatsApp groups going on, even created for our work and other things. But I mean, we used to work together, and we are working in 2 different places now. But we still are connected, sharing, networking. So no, I think it's great because I mean it's a good thing to say that. I mean, when I joined my organization, there was only one Sri Lankan person. So for some reason, it's become like close to half filled with Sri Lankan people, but mainly because of the work quality and the knowledge and other things. So it's really good. I think thinking about 10 years back, we have a big geotechnical community in Australia building up now.
Yeah, good. Great to see. Great to hear that. Yeah. And thank you, everyone. I think it's time to wind up today's webinar presentation. And stay tuned with us on our emails, web, LinkedIn, and Facebook pages. We time to time put updates on our future events. You all are welcome to attend if it is online or in person in Western Australian participants. Thank you, Nilantha, and thank you, everyone, and have a good night. Thank you.
No, thank you, Darshini. Thank you very much. Thanks, everybody. See you.
Thank you. See you.
Thank you. Thank you.
Thank you.